you all for joining for our FriQuant seminar series organized by IHub Quantum Technology Foundation and hosted by IISER Pune. We come up with interesting topics every week in the field of quantum technology, and today we are here to celebrate the World Quantum Day. It was first declared in 2021 and is now celebrated annually on and around April 14 in reference to 4.14, that is the rounded first digit of Planck's constant. You all might know that. World Quantum Day is an annual celebration promoting public awareness and understanding of quantum science and technology around the world. And being a quantum hub of India, we are here to celebrate the World Quantum Day with our quantum algorithm special seminar. And for that, we have with us our special guest for today's event, Mr. Anantha, who is currently an intern at IBM Research. Welcome, Mr. Anant. And now I would like to request our CEO, Dr. Sangeeta Maini, to take the session forward.
Thank you. So, welcome all on the World Quantum Day. Though we missed the day, I think it was on 14th April, but it was declared a national holiday. So, we thought we'll postpone as per everybody's convenience. But I would say, in today's world, I think we don't need a day to celebrate quantum because it's so wide and it's so widespread. I would say, given the launch of the National Quantum Mission as well, I think every day is a quantum day and the future is going to be more stronger in terms of quantum technologies as well. So, you being the young generation, I have high hopes from you that you will lead the quantum mission in the future and gift India the future technologies for India to become a leader in quantum arena. So with that, I would like to welcome you all to this session, and I think more than me, the people who are into this ecosystem at a technical level, they deserve to be speaking here, and I leave the platform for them. So, the project director of IHub Quantum Technology Foundation,
Professor Rahul, for giving us insights of how quantum technology has evolved over the years, and I'm sure there's a long way to go. And moving forward, I'd like to invite our guest, Mr. Anantha, and I would like to give a brief about him. He is a 5th year BSMS student majoring in physics at IISER Pune. His research interests are primarily in quantum information theory, condensed matter theory, and machine learning for physics. He is currently pursuing his master's thesis with IBM Quantum, studying quantum advantage in machine learning. He has also worked on research projects in magnetic resonance, quantum chaos, and quantum box with researchers from IISER Pune, Brown University, and Harvard University. He will be starting his PhD at the University of Maryland College Park in August 2023. Welcome, Mr. Anant, and please continue with your presentation.
Okay, good evening everyone. Firstly, thank you for taking time out to listen to this talk. Thank you for the organizers for inviting me to give this talk. Today I'll be speaking about how quantum computation can algorithmically enhance machine learning. How can one learn distributions using quantum computer models, specifically in machine learning, and specifically within machine learning a class of models called generative models. Before starting, I'd like to thank my advisors and collaborators over this project, my supervisors from IBM Research. The images are blurred, but my supervisor my expert Professor MS Santhanam at IISER Pune and Dr. LV Subramaniam at IBM Research have been instrumental in this project. Without this team, this project would not be possible today. So, with that, I'd like to start with the big takeaway from the talk today. These are the important ideas I'll be introducing over the talk. That is, the main accomplishment of our work has been building a hybrid quantum classical neural network and set up a working implementation on IBM's hardware devices. Through this algorithm, we are able to learn distributions both from a classical source and a quantum source. Over the next 45 minutes, I will define some of the italicized ideas here. What is a quantum classical neural network, what is quantum advantage, and what is generative machine learning. For the first 2/3 of the talk, it will be pedagogical in nature. I will introduce a few concepts and ideas. You can stop me and ask me questions. The last 1/3 of the talk will be key contributions that we have, which I'd like to discuss over based on my MS thesis. With that, I'd like to start with the outline of the talk, how we'll break down today's talk. We'll first talk about the motivation and background on machine learning. I'm assuming people are from various backgrounds and not everyone has the background in machine learning and quantum computation. After quickly reviewing the fundamentals, we'll talk about generative models, particularly a class of generative models called variational autoencoders. Lately, with generative models have been in a lot of not hype, there's a lot of excitement around ChatGPT, which uses transformer based generative models, and we'll talk about a similar generative model called a variational autoencoder. I'll describe how one can derive it very easily and then talk about how quantum correlations can enhance the performance of these models, and then we'll show that how this model can be used to probe advantage in classical distributions and quantum distributions, and we'll see what is easy, what is hard, and what is their quantum advantage. That's the big question. So let's start with what is the motivation and background. I'd like to start off with what is quantum computation and where our work stands off. Without delving into the details, Sir has already talked about the big 4 branches. I've included computation and sensing within the same, and our talk today will be within the realm of computation and sensing, particularly computation. I'm sure everyone knows at this point what a bit is. A classical bit is just a number which is 0 or 1, whereas when one jumps to the quantum quantum bit or a qubit, we talk about state vectors in a 2-dimensional space. Psi is a quantum bit or a qubit, which could be a 2-dimensional complex vector where 0 and 1 are the basis states, and alpha and beta are complex numbers such that alpha squared plus beta squared is 1, mod alpha squared plus beta squared is 1, and such a qubit can be represented on a Bloch sphere, a sphere which is called Bloch, named after Felix Bloch because he did experiments in 1960s on these things. And whereas classically one is restricted to either use a 0 or a 1, when one uses qubits, one can tailor these alpha and betas through processes and make sure that through computations one can move around the sphere on the Bloch sphere and achieve different configurations within qubits. So this is how one would talk about single qubits. Now we'll move on to how a quantum computation can take place, or what is given a bit, how is it useful to us, how do we compute with bits. Now there are 3 essential ideas with a bit. One is a qubit, a gate, and a measurement. These are fundamental entities which is necessary for us to talk more about algorithms or quantum algorithms in general. A qubit is what we have discussed in the last slide. Gates are just unitary operations, or when one says in quantum mechanics time evolution is unitary because conservation of probability and things like that. Gates are unitary, and examples of these are unitary operations on this 2-dimensional space, and these can be represented by matrices in this form as such. So example X is a gate which acts on a 2-dimensional vector, and this is an X gate. H is a Hadamard gate which puts a quantum state in 0 and uniform superposition. And one can talk about these parameterized gates, which are essential for most of today's algorithms, or these are the building blocks of all the algorithms, parameterized gates, where these can be implemented experimentally as well. You have a gate which depends on a parameter theta, and based on certain values of theta you can achieve different configurations. For example, when theta is 0, one gets the opposite of an X gate, whereas theta is pi, you get the X gate. That is an Rx gate, or basically describing how much you want to rotate on a Bloch sphere. Similarly, you have a plethora of gates which can be applied successively on a qubit, and after successive applications you can again get a final configuration of the qubit in an alpha n and beta n configuration. And one more last ingredient in our recipe is measurements. Measurement is an example of a measurement operator is a projective operator. For example, here we have a 2-dimensional system, and measurement operators could be P0 and P1, which basically measure the probability of being in 0 and 1. For example, if we have initial qubit in this configuration, we have a series of gates acting on the initial configuration. We finally have alpha n and beta n, and when one measures it in the 0 basis, the probability of measuring a 0, or after the qubit has evolved till alpha n and beta n and one measures it, you can either get classical values. You either get a 0 or a 1. The probability of getting a 0 is alpha n squared, probability of getting a 1 is beta n squared. So these are the basic ingredients which go up into building an algorithm, and these are the things for one qubit, and one can build upon these things to look at multi-qubit systems. And how we look at it is the same. Along the x-axis we have time, or what operations are happening. Along the y-axis we have different qubits. We have 3 qubits in the system, initially in the 0 state, which is around this state in the block sphere. Say all of them, so you have 3 spheres and each of the sphere is along 0, and then you do a series of operations. H, and this is a 2 qubit gate which is called a controlled NOT gate, and one can, so the question becomes, what set of gates should I apply to get a given measurement distribution. So this is how a quantum circuit looks, where I have many qubits and a set of gates acting on them. Finally a measurement is done to give certain resultant eigenvalues or measurement results, and this can be repeated multiple times to gain, one can tailor this to get desirable expectation values or desirable measurement outcomes and such. With that, I'd like to switch gears and talk about machine learning. I went a little quickly over that part because that was something which I assumed I could cover quickly and people would have a background, but this I'll go a little slow. So within the AI landscape, or what people call artificial intelligence, there are many different ideas. Within, on the left top, if you have artificial intelligence, you have machine learning, which is a subset of artificial intelligence. Then you have deep learning, which is what is state of the art today. Everyone works with, and these are a kind of deep learning models called neural networks, which are the bread and butter of deep learning models. And within machine learning models, there are 3 kinds: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, one is interested in determining or predicting what the distribution of data is. That is, for example, if I have a computer is supposed to learn how to classify objects. If I have 3 objects, a circle, square, and triangle, the algorithm or the machine learns through training examples whether an object is a circle, a square, or a triangle over a period of time. And the 2 types of classification are regression. In unsupervised learning, the problem is much harder. It is now to find inherent structure within the data. Given just a bunch of data, we want to find, are there clusters in data? Within data, are there certain regimes which are anomalous? It's a much harder task, and within that we have algorithms like for clustering, dimensional reduction, and generative modeling. A majority of our work is in generative modeling, which is given access to little amount of data. Can I learn from that data and produce new patterns? It is like how language models also work. Given access to someone giving a sentence, predicting the next word in the sentence, and that is all the generative pre-trained transformers, how they work in generative modeling. Reinforcement learning is more of a action and reward based system, where for a given action you are rewarded, and for a unwanted action you are given a penalty, and you have a lot of work has been done in that area as well. And today we will be focusing on generative modeling. Before delving into how a simple generative AI model, I'd like to discuss how can the notion of qubits assist in machine learning. Machine learning is this technology where has brought a lot of revolutionary changes in many different fields, especially in our natural sciences. And but one fundamental problem is it is not it cannot learn distributions which are made of quantum states, which we will see later, and also it takes a lot of time to train. It takes months and days to train. So one problem which today's machine learning researchers want to ask is, can we have a quantum speed up in machine learning problems? Can quantum technologies help machine learning practitioners? They want a practical solution, whereas current quantum algorithms are all work on contrived examples. Like the Shor's algorithm has a practical solution, but is not possible with today's devices. So within today's NISQ devices, when I say NISQ, that is a term coined for noisy intermediate scale quantum devices, noisy intermediate quantum devices. So these are small systems with 10 qubits, 15 qubits. Can we use systems of such small size, and can we see any effect in machine learning? Is it beneficial for us? And that is the big question which we want to answer in this field. And this is the field of quantum machine learning, and broadly one can look at it in this matrix form, whereas what is the type of algorithm one is using and what is the type of data one has. The data could be classical in the form of images or text, or quantum where one is dealing with data from sensors or data from quantum states and things like that, and the type of algorithm. On the right I have a depiction of generative and discriminative machine learning. Discriminative machine learning looks at learning a decision boundary, well, like classifying between a set of cats and set of dogs images, or say two phases of a dynamical system, and one wants to look at where the phase transition occurs. That's a discriminative model. In generative models, one wants to learn the entire distribution and then be able to generate new samples. I learn the entire dynamical phase of a many body system, and then can I pick up certain points and generate new phases within the system. That is generative AI. Why we choose, or why I've looked at the problem of generative AI is that a lot of research has shown that classical machine learning problems are almost good at everything except this problem of sampling, or there are many problems where one has to sample many random numbers and use it for problems like Bayesian inference, Monte Carlo simulations, probabilistic programming, deep learning, etc. And this sampling problem in machine learning is a bottleneck, and quantum systems or quantum circuits are very good at sampling. They can sample from complex many body distributions and then generate samples from them. So this interacting sampling problem can be enhanced by using quantum circuits. So that is a postulate which has been shown in literature reviews, that generative ML is a space where quantum advantage can be seen. That is why we look at that area now. And also a lot of work is happening in this area of quantum machine learning within physics and within natural sciences, where people are especially particle physics, where you know your sensors in the Large Hadron Collider in CERN, all of them measure quantum particles or trajectories and things like that. Whereas since the data is quantum itself, can we use a quantum ML model to classify the type of systems? Whereas if you can classify, one wants to look at new particles, can we discover a new type of particle, is there a graviton and things like that. I hope there are no high energy physicists here, but I'll talk about what a variational quantum classifier is over the next couple of slides, but it's a lot of work has happening in the last 2-3 years on how can one use these quantum ML models to learn the distribution or to learn the ground state of these these quantum models. With that brief introduction, I'd like to talk very specifically about one kind of generative model called the variational autoencoder. We'll introduce how the model is built, or how one can mathematically formulate the problem, and where quantum models can enhance. This works, okay. So this is next, okay. Thank you so much. So I'll now introduce a simple generative model called a variational autoencoder. We'll derive it. I've skipped the derivation details, but the big picture will be evident. Now the problem of generative learning is as follows. One has access to a lot of data samples. You can imagine X to be a set of images, a large bunch of images, say 1,000, 10,000 images, and labels Y could be the type of image it is. It belongs to a particular category. And the approach that one could do is take a more implicit approach where one can take an implicit approach where one looks at probability distribution and tries to optimize a problem, or a more explicit approach, which is what famously is known as GANs, where generative adversarial networks. And we will look at these implicit methods because these are amenable to our work, and also quantum circuits. One can work with actual probability distributions, and we will see that how one can learn these distributions given just data x. We will discuss a simple approach on how one can look at the joint probability distribution of x comma y, and how neural networks are very good at it but fail at certain tasks, and how quantum mechanics will solve that task. So the framework is as follows. We have access to a large chunk of data x. We assume that there is an underlying process or underlying random variable z which is responsible for producing x, and we are interested in modeling p of x given z, or what is the probability of getting a x given a z. Z is what we do not know, but x is what we want. So at the end of the day, we want to generate x from a z. So that is as follows, and from Bayes' rule we know that p of z given x can be written as follows. We want to finally obtain p of x given z, and that requires us to model p of z given x. Now what does intuitively what does p of z given x mean? It means that we have access to all the x's. We want to know how the z looks given the x. So given access to all the data, given access to all data, we want to know how p of z looks, p of z given x looks, and that requires us to compute this integral here, which is also some sort of a partition function in statistical physics, and it is usually intractable. It usually requires exponential number of resources in time to compute this, and one has to resort to other methods. This p of x is called the evidence, which is called evidence because you have x, and x is the evidence for building the distribution. P of x is called the evidence, and the evidence is usually intractable. So one looks at trying to approximate p of z given x through other methods, and some of the methods are Laplace approximations and perturbation theory, but the one which is the most popular in ML literature or most efficient for our task for optimization is variational inference. Now this is variational inference is nothing but you approximate your p of z given x with another distribution which you know beforehand, say q of z given x. This could be a distribution you know which parameters you could tune. So this is p of z given x is what you do not know. This is called a posterior. I'll just introduce the notion. So p of z given x is the posterior, p of x given z is called the likelihood, p of z is the prior, and p of x is the evidence or the marginal distribution. One is interested in learning p of z given x, but it is intractable to compute. So we look at an easier distribution q of phi z given x, where phi is a set of parameters. Now this could be just this, the p of z given x could look something like this, but we do not know what is the analytical form of this distribution. So we just approximate it to be a Gaussian, and that is the approximation q phi looks something like this, and phi could be the mean and standard deviation of the Gaussian. That is the approximation one is making, and the task then becomes to reduce the distance between these two, between our approximation and what is reality, what is p of z given x. So then we minimize the KL divergence between these two distributions. KL divergence is called the Kullback-Leibler divergence. It's a statistical measure of difference between two distributions. So given p of x and q of x are two probability distributions, the difference or the divergence between the two is given by this. If p and q are the same, then this becomes 1. This becomes 0, and there is no difference between the two. They both are the same. And if there are any differences, this term is non-zero. So if you simplify this, minimizing over phi becomes equivalent to maximizing over this equation, which is what we will come back to later, where we have p of x given z is called the likelihood, and this is the KL divergence between what we have modeled, and this is the prior distribution, that is p of z. So we can assume a form for z, that is p of z, and that is what comes here. So we can assume a form of p of z and assume a form of q of z given x, and this is the KL divergence between the two, and this is an expectation over the likelihood. I will give a more intuitive feel for this formula when we will just go over the neural network framework for this, and with few more approximations in classical ML literature, one arrives at this formula through assuming that this q of z given x has looks like a Gaussian. So, when thinks that it is a Gaussian with covariance equal to 0, then one arrives at a closed form expression here. Minimizing this gives us a solution. So, essentially what we have done is we have circumvented the problem of computing this intractable evidence term into solving an optimization problem which looks like this. And there are many approaches to solving this optimization problem, but like Monte Carlo and things like that, but the most efficient one today is that of deep learning. And I will just give an intuitive introduction to what deep learning is, or what are the essential requirements here. We have deep learning is basically the language of neurons and neural networks, and I will describe what a neuron is firstly. Given what we want here is to learn a nonlinear activation function between an input x and an output y. We have a lot of inputs x and we want to learn the relationship between these inputs and an output y. How do we learn the relationship between these two is where neural networks come in. So, we have a set of unknown parameters called weights and a bias term, and what one does is what one can do is do a linear transformation of the unknown variables x with the weights, and then do a summation, and then we have a activation function. Activation functions are just non-linear functions like 1 by 1 plus x or sigmoid functions as they are called, but this is just one. You can just imagine this to be a non-linear function, not y is equal to mx, but y is equal to f of x. It could be a quadratic function or anything. This is an activation function which does a non-linear transform. So, this is a single neuron. What it does is takes inputs, performs such a linear operation, and then an non-linear operation, and gives a non-linear output, and this output can be coupled to another neural network downstream, and then you will have a structure as follows, where multiple inputs are fed to each neural network here. There is a linear transformation, there is a nonlinear activation, and that is fed to the next layer of neurons, that is subsequently fed to another layer of neurons. So, this is a simple neural network, and here we have a deep neural network. So, there are multiple inputs, there are hidden layers, and there are outputs which aid in learning an inherent learning a correspondence between inputs and outputs without essentially taking what features we like or what features are important. Here one just needs to give the data one has and the output one likes, and these models can learn the relationship between them anywhere. Yeah. With that framework and the framework of the variational generative model we introduced, this loss function I introduced, we can now optimize the loss function to something called a variational autoencoder. The structure is quite straightforward. We have data x and we assume there is a latent variable z which is responsible for producing the x, and we assume, and we have a neural network structure where we have input x. It is being through this architecture of neural networks, we reduce the number of neurons to a small set called the latent variable z, and that again is increases to give back the x here. So, it is basically a structure where a large number of inputs is restricted, constricted to a very small number, and again it is increased back to the original set of variables. And the aim is to learn a hidden representation for the given distribution here. So, if given an input vector capital X which has x1, x2 through x6, we want to pass through the encoder or pass it through this structure called the encoder, get a z1, z2 and pass it through the decoder, which again gives us x1 hat, x2 hat and x3 hat. The goal then becomes to minimize the difference between x1 hat and x1, x2 hat and x2 and x3 hat and x3. So, what happens is one is learning, as one gives an input, one learns the output should be same as the input, and during this process one learns a hidden z representation for each x. This is done by minimizing the loss function as follows. The first term is the reconstruction term, it is called the reconstruction term. If you look at it, it is the log of p phi of xi given z. Xi is the output here given z, z is the latent variable. So, log of this is basically saying minimize the negative log likelihood of obtaining something. minimize the negative log likelihood of obtaining xi given xi, obtaining x2 given x2. And then we have a regularizer term here, which basically gives a structure for the distribution z here. So, if q theta of z given x is what we had a guess for, and p of z can be assumed to be a Gaussian with normal Gaussian, or a multivariate Gaussian with mean 0 and standard deviation 1. So, p of z can be assumed to have a certain structure, and q theta of z given x is what we are learning. Here theta are the set of parameters in your encoder. I showed that there are a lot of weights and biases here, bias term and weight term for one neuron. Similarly, you have those things for all the neurons here. So, when you bring all the terms together, you can call them theta. So, theta is a set of terms in this part of the neural network called the encoder, and phi is all the parameters in the decoder. So, if one minimizes over all theta and phi, this loss function called the elbow or the negative elbow is the elbow is called the evidence lower bound, which is basically the lower bound for the evidence term, which is this specifically when we talked about the evidence term. Here we are trying to maximize a lower bound on the evidence, and this is called the evidence lower bound. So, as one minimizes the negative of that, one arrives at this loss function. Here is the reconstruction, here is the regularization term. And after training, one is able to reconstruct the input from the neural network, and you can get rid of the encoder. You only have this structure, and you can choose random numbers for z and pass it through the decoder and regenerate the data again. So, that is the structure. I hope I went through that in a little detail. And this has many applications in today's world. State of the art systems use it for learning the latent distribution of particles, learning the latent distribution of images on Amazon shopping and things like that. You also use it for anomaly detection and compressing data. This is extensively used in the LHC, the Large Hadron Collider, to compress the humongous amount of data they get in experiments. With that structure there, we know we made a lot of assumptions, and that is what I would want to probe in my presentation now, which is can quantum circuits help in improving the performance of these variational autoencoders. We made a few assumptions on them being Gaussians. Can using quantum circuits improve the performance of such systems? That is what we are interested in. And now I'll move on to talk about quantum enhanced generative models. The motivation is quite straightforward. Quantum mechanics is inherently statistical. What I mean by inherently statistical is a quantum state is able to sample values from a distribution, sample eigenvalues from a given discrete distribution. We know that, and can we use that in a practical way in such a scenario of generative modeling? That is what we are interested in, and this can have a lot of good consequences. For example, one can quantum states can be used to sample from complex many-body distributions. Can we use that in practical applications? And also the states grow exponentially with the number of qubits. If you have n qubits, the Hilbert space grows exponentially in n. So, you have exponential number of parameters coming in. With that, I will just explain a couple of minutes on what a quantum simple quantum variational quantum algorithm looks like. Sir talked about finding the ground state of Hamiltonians. Now, this is a simple framework to find, or this is a simple framework to solve many problems in quantum algorithms as such. This is the quantum circuit structure that I described initially, where one has qubits in reference state zeros and different gates, Hadamard gates and Rx gates, Rz gates. This is called a parametrized quantum circuit. Then you have an objective function which one is looking to minimize or maximize. So, given input and an objective function which one wants to minimize and a circuit as follows, the objective is to minimize the loss function. Now, given this parametrized quantum circuit, we assume this quantum circuit is called parametrized because we have a set of parameters which are to be learnt in the process, and as learning occurs, the loss function decreases, the loss function converges, and we arrive at a set of values theta which give us the desired output. For example, if one is interested in finding the ground state of a Hamiltonian, then encoding encoding the Hamiltonian in this parameterized quantum circuit and measuring the expectation value with different states yields different eigenvalues. The expectation value of the Hamiltonian is lower bounded by the lower energy state. So as you minimize the loss function, one can get the lowest eigenvalue and the eigenstate of a Hamiltonian. Similarly, there are a bunch of other problems, but this is the general framework of a variational quantum algorithm. You have an objective function, you have a quantum circuit whose parameters are unknown, and when an initial guess theta naught is used for all these parameters and there is a measurement performed in different bases, you get an output, and that output is not what we want. So we do classical optimization using gradient based learners, or many optimization algorithms exist, and through that we get a new theta, and that is again there is a feedback loop happening here. Finally, after learning is done, the loss function converges to 0 and we get the answer we need. So this is the structure of a quantum circuit, and through this people have looked at how can we achieve quantum advantage in such circuits, because these are circuits which are amenable to current quantum devices or algorithms which we can run on today's IBM hardware or today's Amazon's hardware or anyone's quantum computers, and can we achieve a quantum advantage. And now I'll talk about what this quantum advantage is like. Basically introduce one sort of looking at advantage and then look at particular experiments where we have looked at. For example, more specifically, a quantum advantage can be defined as a calculation which employs a quantum device which cannot be repeated, cannot be accomplished with a classical set of resources, with a classical computer in a realistic amount of time and energy. So if I can do a calculation with a quantum device which cannot be repeated or achieved with a classical device, then such a phenomenon can be called a quantum advantage. And on the right hand side, I have a figure from a paper by a set of scientists from Google, Amazon and Priskill's group, where this is a quantum advantage experiment where they have shown that a particular quantum machine learning algorithm can achieve, this is Q refers, on the x axis you have the system size or the number of qubits, on the y axis you have the number of experiments required to achieve a certain accuracy 70%. We see that as the number of system size increases, the number of qubits increases, a purely quantum learner or a quantum algorithm requires far fewer number of experiments, whereas a classical experiment has a bound here, a rigorous lower bound underneath which a classical learner cannot achieve that fidelity. So we are on the lookout for such territories or such regimes where a quantum learner can get a fidelity or get an accuracy like this, which is unattainable by a classical learner. That is what we are probing for. And so now with the introduction of a variational quantum algorithm, a variational autoencoder, and the evidence lower bound, we want to ask 3 questions, and this has been the theme of my master's thesis over the past year. We want to ask if quantum generative models can encode complex distributions. Can we have an improvement over the evidence lower bound in traditional variation autoencoders? That's one question. The second question is, can quantum circuits help in efficient sampling? It is well known that classical models are not very good at learning quantum states. One requires exponential number of resources to learn these. So can these quantum circuits help in doing such task, a task which is intractable to classical VAEs? To address these 2 questions, we explore 2 applications of a QVAE algorithm, which I will describe in the next slide, which is a quantum enhanced VAE. How we enhance it is in the next slide, and we look at 2 applications, looking at classical data and looking at quantum compressing and general distributions which are intractable to classical methods or quantum data, and that encompasses the last 2 parts of my talk. Now we will look at can quantum enhanced variation autoencoders learn classical distributions, and we know that it is easy for classical methods to learn it. A classical algorithm can learn classical distributions. That is what all the machine learning excitement is about. We will address the question here, and then we will look at how can we learn quantum distributions. As a proxy for a classical distribution, we look at these MNIST images. that is a set of images of zeros and 0 to 9. Particularly, we will look at 6s and 9s because these are the most difficult digits to distinguish in a realistic task. And we look at can a quantum encoder, or can one use a variational quantum algorithm which we described previously, can we use that to approximate the elbow loss better than a classical encoder. And the goal here is to produce such images with quantum computer. So, can we use the atoms in a quantum computer to produce such images? And this is the structure we proposed in our work for a quantum enhanced VAE. The structure here is the classical VAE. Now, the classical VAE contains of an encoder, the structure which we discussed earlier. It has a latent space and then a decoder. In our problem, we have a quantum VAE where we have a quantum circuit with states initialized in 0, a set of parameterized operations and a measurement that yield a discrete distribution, and samples from these discrete distributions are passed through a decoder to again generate samples. The goal here is simple. Given digits, given a lot of data of 6s and 9s, we do a principal component analysis to get the principal eigenvectors of a set of images. Can we pass these images through a quantum VAE and a classical VAE and generate outputs? And if after we generate outputs, how do they look like? Are they comparable? That is the question we are interested in. Before I go that, let me just explain how the process is. So, if we have a 6-digit or a 9-digit, it is broken down into 5 principal components, and that is passed through the quantum encoder, and measurement yields a discrete distribution, and that passes through the decoder. And what one expects is, as learning happens or as the algorithm progresses, the loss functions should decrease. One should be able to produce realistic images, and this is a result of how training these QVAs looks like. So, we have the total loss here, which is a sum of the mean square error loss and the KL divergence loss, and the epoch number is the number of repetitions of the experiment we do. So, what we see here is that as the number of experiments are repeated, the loss function decreases. That our model, that means our model is learning the representation of the digits. So, as we give a 6 number, the model is able to reconstruct a 6. As we give it a 9, we are able to reconstruct a 9, and as follows. We see that this the original to the reconstructed one is quite clear. In fact, here it is a bad 9, but we are able to reconstruct it in a better fashion. And after this is done, we throw away the quantum encoder, that is, one can, after training is done, one can get rid of the encoder and only generate images from the decoder, and that is what we look at. So, after training is done, one can generate a set of new images of 6s and 9s. Now, these look quite noisy because there is a PCA transform involved, and by choosing random bit strings, so each bit string corresponds to a certain kind of image, and one can use a linear combination of these bit strings to get a new number 9 from the new number 9. Like the data we use was 6s and 9s, and after the experiment is done, one can choose random numbers, feed it to the decoder, and we will get an image 9 or 6. But we are not done here. We need to compare with classical models, and classical models do very well at these tasks. So, if we are given the same data set of 6s and 9s, and we pass it through a classical model, it also performs very well, the classical VAE. As the number of epochs, the number of experiments are repeated, the model learns, the loss function decreases, the losses decrease. The combined loss is a weighted average of the KL loss and the mean squared error loss. This is the loss on another set of data called the validation set. We can see that after training is done, each input image is reconstructed quite well, and even the validation set, that is, these are a set of images the model has not ever seen. So, if I give a 9 here, it is able to reliably reconstruct a 9, and after training is done, we can generate new images. We just give random numbers to the model, and the model is able to reconstruct 6s and 9s quite efficiently without noise. Here the pixels are much more clearer without noise, and classical models do very well. So, in the first part here, we have seen that we compared the performance of a quantum model, quantum enhanced model, with a classical model on classical distributions or classical data sets, and we found that classical models do really well. and quantum enhanced models tend to do comparatively similar, but do not give us any advantage as such, or do not give us any performance enhancement. That is what one looks at the first place. With that in place, we will look at this example or this set of this problem where classical models do not perform very well. That is the set of quantum states. So these distributions are known to be hard for classical models, and we want to know if our quantum models can perform better. As sir mentioned initially, simulating these classical models requires an exponential number of parameters, and simulations run for many days. We want to know if our model here, the quantum VAE, can it do better than the classical VAE? Can we compress the representation of quantum states, and how do we do it? Or how good is it? Can VAEs compress these states, and what are the number of parameters required? How do the parameters scale? More specifically, what kind of quantum distributions are compressible via our VAEs, and how do the classical models perform? The kind of distributions we look at are as follows. So the framework we are looking at in this part of our experiments is as follows. As an experimentalist, one has access to a lot of quantum states which is coherently produced by nature. So nature repeatedly produces a set of quantum states rho, which one has access to, and one is interested in obtaining this state in a quantum computer or a quantum device which can do simple calculations. So can we take a quantum state here and use it for downstream tasks? Now there is a theorem called the no cloning theorem, which does not allow us to copy this state into this state without any other changes happening in the environment. And what we are interested in our problem is, as we go on measuring the quantum state, one has access to all the bit strings or the set of classical values a quantum state gives. And if given these classical values, can we reconstruct the state with a quantum enhanced model? Given a quantum state, perform multiple measurements on it, and can we reconstruct the measurement distribution of this quantum state? That is the problem we are looking at here. So B, the figure B here gives a structure for a quantum enhanced variation autoencoder, where the structure is similar. We have an encoder which is classical, we have a latent space which is continuous Gaussian like, and we have a decoder which is a quantum circuit as we described earlier. C represents a classical variational autoencoder with classical neurons in the encoder and the decoder. The objective here is, given measurement data, can we reconstruct the measurement output? And we look at different kinds of states here. So now I'll talk about the different kinds of rhos we use. Now rho is a density matrix, but one can also look at pure quantum states, which we have looked at 4 kinds of quantum states in our experiment. The first one is are called product states. These are states where there is only classical correlations involved. So you can imagine this as one qubit. This is another qubit with no correlations involved, and you have a set of operations performed on this qubit. There is no correlations between them, and if you have an n qubit product state, the number of parameters required to describe this state will be 2n. It is linear in n. This is one set of states called product states. These are the other set of states we look at. These are called quantum circuit states. This is simply a set of quantum circuits with a defined entanglement structure. Now the entanglement structure here we use is linear. What it means is that consecutive qubits have entanglement between them, or have a control NOT gate between them. Now this is specifically amenable for today's quantum devices because they don't have all-to-all connectivity in real hardware. So these are the set of states we look at, and we look at states where this can be where we have an original state where this structure is stacked and repeated multiple times, and finally a measurement is performed, and such a measurement gives us a discrete distribution. And the third set of states are called Haar random states, which are basically a general quantum state where it could be state sampled uniformly on a sphere. So you have a sphere and you sample uniform probability distributions and get entries in a 2 power n dimensional system. And the fourth one is a dynamical system called a quantum kicked rotor, which basically is a system where is basically a system where one observes chaos in the classical limit, but when one looks at the quantum limit, interesting dynamical properties emerge. Our interest here is to know if we can reconstruct a measurement distribution. For a specific example, if one has access to the one has a state, for example, when we look at these product states, we assume a product state as follows, and one has access to only the measurements. So there is a product state in nature which is something like this, and an experimentalist has access to all of these states, and they perform a sequence of measurements in different bases, and we consider here only one basis, say the Z basis, and when measurement is performed, one gets results like this, and we want to know what state produced this, or can we reproduce this measurement distribution. This is where our algorithm comes into picture. Given access to this measurement data, our QVAE algorithm, as we train the model and minimize the objective, the loss function, is able to recreate the measurement distribution. As the number of epochs or the number of repetitions of the training data is increased, or as we train the model, the fidelity between the two distributions, fidelity is basically this metric which tries to maximize the similarity between the two distributions. So initially, as the model is training, we have a distribution over all the 16 states. So we have these masses here everywhere, and as training occurs, the mass gets concentrated here, and the quantum circuit we have, or the circuit structure we have here, changes. The parameters here change such that the overall loss function decreases. So as that is performed, the distribution produced by our model mimics the original distribution, and we are able to learn this task. And similarly, for a different kind of state, we look at Haar random state, which are states with inherent entanglement within them. Our quantum VAE model is able to reconstruct the original distribution. So you have a random unitary matrix which acts on a zero system in state 0. It's a many body system, a 4-qubit system, and when one measures it, has this distribution, and this distribution is sequentially fed to the QVAE algorithm, and after training, the classical part can be discarded and only the quantum circuit and the parameters remain. So one can go to any quantum computer and implement these gates, and this distribution is recreated, or one has the essential parameters which recreate the distribution. So the true one is blue, and the orange one is the one produced by the quantum circuit after about 10 or 11 epochs. The fidelity is about 0.55, about 8.55. Yeah. This is actually universal across states, all kinds of states. But the most interesting aspect here is if you look at the difference between a classical VAE and a quantum VAE. For product states, there are no non-classical correlations. That is, one only looks at states which are easy to learn, and you see that classical VAEs perform really well. When one compares the performance between classical and quantum, the classical VAE performs really well, and it works well for 4-qubit and 8-qubit systems. The seed here refers to different random initial states which we have used. But when you come to quantum circuit states, Haar random states, and kicked rotor states, we see a stark contrast between those from a classical VAE and those from a quantum VAE. For quantum circuit states, for example, the performance is not very different from a uniform distribution. A uniform distribution just says if I assume the distribution to be uniform and then I start training, or if that was my guess, I would have a fidelity of 0.477. Whereas a classical VAE can get a fidelity of 0.51 at best, whereas a quantum VAE can get a 0.981 fidelity. The maximum one can go is 1. We see that in all cases where there is entanglement within the inherent quantum state, the quantum VAE outperforms the classical VAE, and it is evident in almost all cases. Similarly, within the quantum kicked rotor case, where there is a stark contrast in most of the, especially the localized regimes for 8 qubits. And one more fact is these quantum VAEs only use linear number of parameters n, whereas all the classical VAEs require an exponential number of parameters, or number of parameters in the decoder to produce these distributions. And this is practical as well. We have implemented this on actual IBM hardware, and these results are from simulators, but the real experimental results also show similar outperformance over the classical VAEs. And now so far our work is also supported by theoretical work. which is focused largely from a mathematical perspective, where one uses information theoretic principles like pack learning, that is probably approximately correct framework, to see if can we learn these discrete distributions produced by local quantum states. And one common conclusion which all these papers point out is that to learn the distribution of a quantum state, one needs access to quantum resources, and simply a classical resource or a classical device is not capable of learning such a distribution. Now these papers give mathematical proof that our model is able to learn, but they don't suggest any model which is able to learn. They point out to quantum fault tolerant devices, that is devices with have millions of qubits which can able to do this, and ours is one of the first purely small quantum algorithm with limited number of qubits which can show like this difference in performance. With that, I'd like to share what we can conclude from the talk. The story so far is that a quantum VAE or a quantum variational autoencoder is able to reconstruct MNEST images or images of 6s and 9s with far fewer parameters than a classical device, but we don't see any measurable difference in the kind of images we produce or the kind of output one produces with classical distributions. Classical models are much better than quantum models on classical data. However, when one looks at entangled states and product states, our model performs is able to give a very high fidelity and it works on real quantum hardware as well, whereas classical models fail to learn these with very high fidelity. They fail to learn the structure or the measurement distribution of these states. However, the algorithm has many tunable parameters, for example the latent size, the learning rates, the patience factor and things like that, which one can tune. I did not go into those details in this talk, where one can tune many of the parameters of the model itself and the right parameter regimes. How should we tune the set of initial structure of the model, the number of neurons, the number of quantum bits one would need, that has to be determined through many semi-empirical trials. With that future, one can look at probing these theoretical quantum advantages, where one can say that how these discrete distributions produced by small local quantum circuits, how can one show theoretical advantage in small quantum circuits. And also we will focus on learning distributions of more complex states with real hardware. Right now we are in the process of running these on real IBM hardware, and the performance decreases on real hardware. So one has to resort to classical error mitigation techniques like dynamical decoupling and things like that to reduce the error rates in these devices. So can we show that with these hardware, and also look at how the number of parameters scale with the number of qubits, and how is the performance, and what is the mutual information and things like that with Z and X and things like that. The big picture is that quantum ML is a blue ocean today. Like a lot of new opportunities and ideas are sprouting every day on arXiv and different journals, and a lot of things are yet to be explored. And with this talk, I hope I've given some ideas on which different ideas one can look at. With that, I'd like to conclude my talk. And thank you so much.
Thank you, Mr. Anantha, for such an engaging informational session on quantum machine learning. Do we have any questions? If there are any. All right.
I'm sorry, I removed the mic.
No, it's okay. So, I mean, this kind of scheme of optimization,
Yes.
One can do it with any quantum system. I mean, forget about qubits or anything, but if you have a collection of quantum particles,
Yes.
and then you have a control on, say, doing some unitary operations, and
Yes.
then can one formulate the sequence in such a manner that you get to a problem similar to, say, this annealing problem or something?
Sir, yeah, there are a lot of ways. This is what you're talking about is called physics-aware training, PAT. There are a lot of approaches. It's similar gradient based. So Yeah, and this can be done. There are a lot of papers also on this approach, where you have a dynamical system you can control, but it's very hard to model it on a computer. So,
Right.
so you can actually do the forward propagation, the neural network structure I showed. You can do that with the real hardware and then minimize the loss function, the objective function. This can be done. There are this is called physics-aware training and schemes for that.
How many qubits machine do you access? Do you work?
Yeah, so it depends on access level. So I had access up to 32 sometimes, but that is again limited access. You have educator access and things like that. But as for free, as in when one starts, you can use up to 8 qubits. Yeah, these are like real hardware with a lot of noises and.
How many are noise free actually?
No, there is no noise free machine.
Yeah, that's true.
So, but you are working with the IBM team,
Yeah.
right? They
Yes,
don't
sir, I
have
have.
access.
So even they have.
Okay, you can
Yeah, the IBM team has access, but for me to execute them, we'll have to show it theoretically that it is possible here and all this. Then we'll have to execute it on real hardware. And also, learning on hardware is very hard. It takes you, it is not possible. So what one does is, you train everything on a simulator, you get the parameters which are true, and those parameters are executed on the hardware.
So what will you gain?
Sir?
So what do you gain?
So on the real hardware, one is able to show that there is a difference in fidelity.
I didn't understand.
Right, sir. So
No, you compare between the simulators and the real hardware.
right, yeah. So
There, do you apply any any error correction when you
yes,
run it
yes,
on a-
yeah. So on hardware, so what happens is so on a classical simulator, like a lot of it's called stabilizer states and things like that. One can do simulations up to 75 qubits on a computer, like a laptop of mine or a supercomputer. And after
Now, how many qubits you can do?
there are kind of states, you can do 70 qubits also. That is a restricted class of states. But any general you can do 32 qubits. So for 32 qubits, what one does is as you train, as you minimize the loss function, you can learn these theta 1, theta 2, theta 3. So after your training, you will have access to these values, say 3.1, 1.2, 1.3. So then you can go to a quantum hardware and you can set these gates to be these, and then execute it on the hardware. The hardware results will not be the same as what you get here, but you can also choose to do like error mitigation schemes, error suppression schemes, which is readily available in the software packages. I had to write code for a few things, but it's ready. It's very fastly being developed.
Do you have to wait as well when you put in your codes?
Yes, yes.
How long is the wait?
So it depends on what kind of access you have. So initially, if it's an access to it's open source, right? So anyone can go and access. Depends on how much time. Sometimes an experiment like this takes 50 minutes. Just running it on hardware and getting results, not even training. So that takes 50 minutes. Sometimes it takes a minute. But that is the range I have experienced. And it also depends on which device and what are the noise. Noisy devices with a lot of noise, they have very little waiting time. So devices which are pristine and good, they have a lot of waiting time. So if they are, and even premium access, they have a lot of people know access. So even that has a lot of waiting time.
Have you tried running on other platforms as well?
No, only with IBM's devices.
Can we use your work in quant trading?
You have,
This techniques that you mentioned.
yeah, the techniques can be used anywhere. But then why would you use a quantum algorithm for a task where the classical models do really well? Now that is one thing which is really important, right?
Do you have that thing?
Yeah, so one of the takeaways from my talk here is that quantum models will show advantage for quantum states. Quantum machine learning will be beneficial when one uses quantum states to learn things. If one is using classical datasets, classical models are very fine-tuned. I mean, you have six decades of literature working on classical models. So when you want to look at quant trading and things like that, there are approaches. JP Morgan, CS, Goldman Sachs all have departments working on these. And it's really hard to have any speed up when one looks at quantum models for instance. Good question. I mean, they are still working on it. Thank you so much.
So with this, I would like to invite Dr. Sangeeta Mani to present our guest with a small token of appreciation.
What else? You want to join? Please come.
No, please go ahead.
Please come.
Please go ahead.
Yeah, thank you so much for the wonderful talk. Thank you. Come, you too come.
Thank you.
Thank you. Thank you all.